down to various hydrolysis, either base or acid hydrolysis reactions, so on and so forth. And then the specific name of the type of reaction that was being handled. And then we divided things up into the chemistry, and these measures are relative, right? So we created this giant training set, and we compared these things relative to other chemistries. So it was chemistry, mass, energy, and solvent score. So the red, yellow, green was a very quick and easy way for chemists to say, okay, this is better than, approximately than something else. Yellow is and red, you probably don't want to go there. And the links, each one of those chemistries would take you down to a lower level. And what we tried to do was give best practices. So for a given type of chemistry, what were the best practices among all the different examples of that chemistry that we had? Then we scored them, and again, that's a relative score of the chemistry. So again, trying to give people specific guidance around the chemistry that they were trying to do. We also did this with technology, all right? So I've been talking about the integration of chemistry and engineering for years. Engineers get this, but chemists don't. Synthetic organic chemists are extremely resistant to chemical engineering. So what we tried to do was to create a guide which would be extremely easy for your typical synthetic organic chemist to do, and it was aligned towards the kinds of processes that you would do in a particular synthesis. So whether it's a phase separation or a resolution step or whatever, we would rigorously compare different alternatives. If it was a reactor, we did a standard batch reactor, a mini reactor, and a micro reactor, and we would compare those kinds of things. This, like the chemistry guide, red, yellow, green, parameters, environment, safety, efficiency, and energy, and you could click on those particular types of, say it's a phase separation. If you clicked on phase separation, it would take you down lower and give you the case scenario comparison in great detail. So again, what we tried to provide people is the reason behind why it is that something wasn't green, because many times people don't agree with or understand, but if you make it transparent, then it's harder to argue with. The first tool that we ever developed, and this was largely driven by the fact that solvents, we found very early on, were driving a lot of the overall greenness of a synthetic organic process. And this guide has gone through probably 4 iterations at this point. So this is not the most recent version. They're up to more than 100 solvents at this point in time. And the way the guide is constructed is that on the left hand you have the class of solvent that you're looking at within any range of solvents. So you can see in the alcohols it ranges from ethylene glycol to methanol. And then we evaluated them according to waste, impact, health, safety, and life cycle. Each one of those categories, waste, impact, health, and safety, so forth, have sub-elements to them. So it's a range of parameters that we're evaluating that ultimately were scored and rolled up to that particular score. Each one of the solvents, if you click on, will take you to a series of screens where you can get further information. So these are the subcategories in each of the areas. So recoverability and recyclability, disposal issues, VOCs for waste. There were impacts to water and to air. The impact in terms of fates and effects to organisms, either air or in water. The health, largely based on risk phrases, and safety ultimately was whether or not things catch fire or whether or not they explode, and a number of other parameters besides that. So again, a single page, very quickly, a person can determine whether or not something is green without a lot of effort, not too many clicks. So if we clicked on 2-propanol, again, you can go down, you can get into physical property and azeotrope information, you can get into separation by distillation data, and life cycle get guidance. And again, You can actually do what-if scenarios. So if you recover so much amount of the solvent, how does that impact your life cycle score? And energy, and you can look at details around the scoring and overall life cycle information. We also did this for bases, because bases are used quite a bit, as you know, in synthetic organic chemistry. So we ranked 42 bases. Flask is our life cycle tool. And again, this took us about 6 years to develop. What this was intended to do was to allow chemists to input their materials of use in a particular synthesis and get a very rapid scoring of how one way of synthesizing compared to another way of synthesizing a particular compound. So again, you would just basically put in the material that you were using, the amount in terms of the mass. You would have to classify it. We had ultimately 12 different categories that we used to classify the particular compound. The reason we did that is that you can't get coverage for all of the compounds that might be used, but what you find is that compounds that are very similar in structure many times are made in very similar ways. And the life cycle is very similar. And we validated this, and it worked. The other thing at the bottom here is that it would automatically calculate the mass intensity, the mass productivity. It would calculate the solvent score, which was based on the solvent selection guide, and then it would also calculate your reaction mass efficiency. So again, people who know how to use this particular tool, it only takes them 5 minutes to do this. So you can get a fully burdened life cycle within just a few minutes of effort. The other thing that it did is it identified the largest mass contributors and the largest energy contributors to your particular synthesis. So again, one of the things that we found is that mass and energy are very closely correlated to each other in terms of greenness or determining greenness. And if you think about it, if solvents are the biggest driver, what do you do with solvents most of the time? You heat them or cool them. So it's driving the energy. So they almost become proxies for one another. The other learning that we found over and over again is